Okay, I guess we can get started. So it's, I think the university I joined is UVA, but then our class is becoming more and more Caltech because on average Caltech class are like 5 to 10 people. And then, we are at that very elite size now. And one thing that, we will add to the, one thing we will add to our class is at the very beginning of each lecture, we will add a kind of a short 10 to 15 minutes presentation on some of the cool tech that happening, around the world. And then the cool tech I'm referring to is not like Apple Watch, Tesla car, it's not those. But then the cool tech that are really happening in the university and then some research institute that pushing the world forward. And then it doesn't necessarily have to be related to our class, okay? Because from what I've seen in UVA, well, at least in ECE, is that undergrad, our students, especially undergrad, actually don't have access to the latest research in the world, right? We don't have an organized seminar to introduce those things to you guys. So I think like our quantum computing content is a little bit dry, okay? And then so we can spend 10 to 15 minutes on this. We had this section in the 2 previous semesters of the same class. And then at first I thought that we probably don't want to do be on this online section is because we have 1 week short compared with previous semesters, and then also online class are usually a little bit slower. Okay, the pace of the online class a little bit slower, and then also we have 1 week short. So I'm not sure that we have the time for this, but then, I think given that the class is going to be harder and harder, from this on, I think it's worth to spend 10 to 15 minutes to kind of explain, okay, a little bit of other stuff. And then I originally intend to start this section with the IBM quantum Q computing, but then I think we have 12 students registered, and then right now we only have 4 here, so I don't want the other 8 to miss the IBM quantum computer tech intro, because that's kind of the one of the 2 tech that's actually related to this class. So today we're probably going to discuss. I can show you guys a little bit of what is the resonator. Okay, today's resonator are optical cavities. Right, we learned this in the quantization of light, saying that okay, there's a pair of mirror. Okay, and that's it. But then the fact is that it's never really a pair of mirror, and then it's actually really, really interesting. It has many different variations. Okay, now let me put my computer to share screen mode. Okay, so let's come back to our class content. It's using the last week we introduced that we can use linear algebra to typically the vectors and matrix to represent the eigenstates, and then of course eigenstate and then arbitrary state, and then use a matrix to represent the operator. And then now when you need to calculate the expected value of your operator, which corresponding to a measurable physics quantity, then what you do is that you do a left bracket, right bracket, and then in the middle is your operator, which means the inner product, okay, between these 3 things. And then when you write it down, it's simply a matrix times a vector and then another vector, okay, and this gives you the expected value of the operator. Now, I want to give two examples of how to use this linear algebra representation, okay, to express the systems we have discussed about. So the first one is, well, both examples are actually trivial examples. The first is that, okay, suppose there's a Hamiltonian, okay, of the quantum objects. For example, our infinite potential well, and then you also have your eigenstate psi n. And we know that because this is eigenstate of this Hamiltonian, so that you always have your Hamiltonian act on psi n. Okay, give you En psi n, right? Just on your eigenvalue, okay, or the eigenenergy of the system. Now the question is, okay, if we write down the eigenvalue as this base vectors, okay, 1, 0, 0, 0, 1, 0, 0, all the way down, then what would the Hamiltonian look like? What would the Hamiltonian matrix look like? Okay, and the idea is, to solve this is actually quite straightforward, because we know that the matrix element for an operator, okay, the jth row, kth column element, is just to do an inner product of A act on psi k and an inner product with psi j. Okay, and so the element of mth row and then n column of the operator of Hamiltonian is simply inner product of psi m and then h, the Hamiltonian act on psi n. Okay, and then we already know h act on psi n because psi n is the eigenvalue of, well, eigenvector of the Hamiltonian. So this gives you a number of, and then times the eigenvector, so that this gives you to this. Okay, and then because En is a number, so you can pull that out, and then you get En psi n psi n, right? And then we know that this is simply means the inner product between two eigenstates, and if m equal to n, this is 1 because the eigenstates are perfectly normalized. And if m is not equal to n, then this is 0 because eigenstates are orthogonal to each other, right? So you have En, a delta function, m n, okay, or equal to En equal to m, and then 0 and not equal to n. Okay. And so because of this, and you can see that HMN is the matrix of the Hamiltonian is very easy to express. Okay, so when n equals to m, it's non-zero only when n equals m, and when n equals to m, it means that you're calculating those elements are actually diagonal elements. Okay, so for the first column, first row is E1, the eigenstate of the eigenenergy of the ground state, and then the second row, second column is E2, okay, first excited state energy, and then all the way down to En, and then all the other values, are 0. Okay, so this is a matrix representation of the Hamiltonian. Okay, if you use the Hamiltonian, if you use the eigenenergy states, okay, as your vector basis. Very, very straightforward. Any questions here? Okay, now the second example is even more trivial. is the identity operator. Identity operator is defined as if it acts on any wave function, okay, it will give you the wave function itself. Okay, it will not change the wave function at all. So it's called identity operator. And then you can almost immediately imagine that the identity operator must be identity matrix, right? Because if you learned linear algebra before, you know the identity matrix is this. All the diagonal terms are 1, and then non-diagonal terms are 0. Okay, and then in linear algebra, you know that identity matrix multiply any vector equals to the vector itself. So this is called identity operator. Okay, and then the same idea can be applied to other operators, and then you can use the same method to calculate the matrix representation of other operators. And then now you see that the difference between operator and operator are no longer like, they have different different form, but it's simplified or unified to the matrix form is that they have different matrix element. Okay, so they're the same form, but then numerically their number is different. One more thing that I want to add here is the identity operator. To probably it will be to your surprise, this identity operator is actually kind of very useful in quantum mechanics. Okay, it's if you think about it, what it means is that it's actually the one, one in your system. And but then this one is not the numerical one, but then it's a two-dimensional one. Okay, it's a matrix one, and then so the identity operator, identity matrix, are usually used to express. the are usually used to express other operators. For example, okay, let me show you guys what the identity operator also can write down as. So identity operator is 1 for all diagonal components, 0 for all other components. So identity operator can also be written as in this form. Okay, so what this means is that this is very different from what you used to learn is that what you used to learn is left bracket is on the left, right bracket is on the right, and then when they meet, it means inner product. Here is that the right bracket is actually on the right. Right bracket is actually on the left, and left bracket is actually on the right. Okay, and why this represent identity operator? Okay, we can actually apply this on arbitrary wave function. For example, a wave function of alpha 1, alpha 2, all the way down to alpha n. Okay, and then we can kind of show you guys that this act on any wave functions must return to the wave function itself. Okay, so we can write this down as first just use plug in the identity operator. Okay, and then this act on arbitrary wave function, and then this wave function, if you use wave vector, if you use the Dirac notation to express it, okay, it's actually the linear combination of all the eigenstates, eigenvectors, and then the coefficient is alpha 1, alpha 2, all the way to alpha n, right? So psi n okay, alpha n. Okay, and then we know that this alpha n is just a number, so you can, be bring to the front, and then also the a sum. Okay, you can switch the order. Okay, you can change the position, so that what we can do is we put the let's see. Let me get the notation the same as my note. Okay, so this is M. So for the identity matrix, it's n equal. Use the index of n, and then for the arbitrary wave function, use the index of m. Okay, and if you bring the alpha number out and then switch the order of these two sum, what you will get is, okay, a sum of m 1 equal to from 1 to n of alpha m, and then a sum, okay, of n from 1 to n, psi n, psi n, psi n. Okay. What we do is just we switch the order. Okay. And then now you can see that, okay, appears something that computable for us is the inner product between psi n and psi m. And we have seen this many times, is that, this is the delta function. It's 1 when n equal to m, and then 0 when n not equal to m. Okay, so okay, so so if we only keep the term that is non-zero, okay, which means n equal to m, okay, n equal to m, okay, this term would be 1. Then you have alpha m, okay, psi m, right? Because here we already let n equal to m. That's the only non-zero contribution. And now if you look at this, okay, this is exactly the same. If we write down psi, here our precise is, right? Right, we use psi as this. So if you look at this, the result is exactly the same as psi itself, right? So it looks like you did nothing. Okay, you did nothing to your state. And okay, we just show that, okay, this is identity matrix. Can also be expressed in this form. And you might wonder why this is important or why this is useful. It's actually because for a lot of matrices that we actually use, the majority of the elements are 0. So we actually rarely write down the matrix itself, but rather we just pick up the terms that's not 0. Okay, so this is a good way to actually write down the terms that's not 0. Okay, if you think about it, is that because you have made n equal to, well, these two indices the same, so what it's really meaning is that, okay, these are the terms that are diagonal. Okay, the first element, the row equal to the column. Okay, the index of the row equal to the column, and then the coefficient is 1. Right, that's how you read this. And this is much more easier than write down a huge matrix that is n by n. Okay, and then the same can actually be applied to other operators. For example, a. Okay, then how can we express other operators? Okay, in a similar way like this, so that we can avoid writing the huge matrix. the thing that you actually can do is actually very simple, and it's a little bit, kind of, I would say a little bit surprising, is that what you do is that you multiply identity matrix on the left, and then you multiply identity matrix on the right. So typically you're doing nothing, okay? You're really doing nothing. Then you plug in the expression of identity matrix. Okay, you plug in this into here. Okay, then you write down this expression. Then you will see that on the left is identity matrix n from 1 to n. Okay, psi n, psi m. Okay, sorry, this is also n. And then you have the matrix, you have the operator A, okay, and then you have another identity matrix, which is m, 1 to n, psi m, psi m, okay. Then one thing now you can see is that, again, the same trick we do is that to move the sum, okay, to the front, that you will have n equal to 1n, also m equal to n1, and then right bracket n. Now this, right, we're just simply writing this up and then copying all this except moving the sum to the left. Now this also appears something that whenever you do this, okay, whenever you plug in something like this, it will always somewhere will appear an inner product, right? Because you see you have left bracket, you have right bracket on the left, and then you have right bracket on the left, right? So when they meet, it's actually an inner product. So this is the inner product. Right, if you look at this, this is the same as the matrix element. Right, the matrix element of jth row, kth column is actually just the inner product of psi j and then A act on psi k, which is also writing as the the integral of psi j conjugate A and psi k. Right, so this is what we talked about in the last class. So you see that, so this section here is the matrix element of A, N, M, right? So you have a matrix element here. And then if you see this as a matrix element, so it's a number, and a number can go in the front, right? Number can be moved left and right, so that you move this number in the front, and okay, the sum is right down here. You have A, N, M. Okay. So your matrix A of your operator A can now be expressed in this simple form, is that for the nth row, okay, nth column, the matrix element number is A, N, M. Okay, A, N, M. So this is the way that the physicists use to kind of be convenient or be lazy, right, to write down a matrix. And then I can give you guys a very simple example, is that there's an interaction, Hamiltonian or matrix that is very common. Is called, it's actually like this. The diagonal term is 0, off diagonal term is G, and then I think you will see this in one of your homework. What it does is that it's able to flip ground state to excited state and excited state back to ground state. It's acting like a NOT gate. And it's actually quite easy to see here is that okay, if you look at this matrix, right? If you put a G in the front, you look at this matrix, and then if you act this matrix on, one of the eigenstate, for example, 1, 0, then what you will get is, first column times first row, first column, 0, second row, second column, 1, right? So you're acting like a NOT gate. You flip 1, 0 to 0, 1, okay? And this matrix, you can write down this matrix in this way. It's true. Also, you can write it down as, okay, you can also write it down as G, okay, psi 1, psi 2 plus G, psi 2, psi 1, okay, psi 2, psi 1. And the good thing about this is, well, first, you don't have to write down matrix, and the second thing is that it's very, very clear what will happen when you apply this Hamiltonian onto a state, right? For example, if you apply this Hamiltonian on this state, psi 1, right? Psi 1, okay? Then what will happen is that this, okay, the first term act on psi 1, you will have psi 2 inner product with psi 1. That's 0. So this term goes away. And the second term is that psi 1 inner product with psi 1. So this is 0. This is 1. So this term will stay. And this term stay, and then the remaining you get is psi 2. Right? So it's very clear that when you're writing down in this form, what this matrix means is that, okay, this will flip ground state to excited state, and this will flip excited state to ground state. Okay, so there's actually a physical meaning of this matrix element, and it's relatively straightforward to see them if you write it down, okay, in the Dirac notation rather than a complete matrix. Okay. Any questions? Okay, good. There's a more detailed example in the lecture note, page 17, about this interaction Hamiltonian, okay, between state 1 and state 2. And I'm not going to repeat it here because we just covered the gist of the entire thing. And then, now let's jump to another thing that we have to cover. Okay, is quantum number. If you feel that the previous lecture and this lecture is a little bit not well organized, that's normal. It's because we're talking about mathematics, and then usually they're just definition after definition after definition. So if you ever take, I hope you will not, but if some of you want to torture yourself, you can try group theory. Okay, it's just the entire class is definition, definition, definition. It's like, unless you're really gifted in group theory, but I find it to be rather disturbing, and then I fell asleep all the time in group theory class. Introducing the kind of the notation and then the mathematic foundation of all this math related to the quantum computing is kind of like a mathematical class, and then I will try to get it over as quick as possible. Quantum number, okay. So quantum number, we never really officially introduced them, but then you kind of been using them all the time. This is the quantum number, okay. The n here, the number that you use to label, okay, your eigenstates. Okay, these are called quantum number. And then the reason that we need to officially introduce them here is because in quantum computing, okay, or later in the qubit, because we're simply using ground state, excited state, second excited state, we're no longer using wave function at all, so that quantum number, okay, is the only thing that indicate what state you're in, right? So quantum number now it become very, very important. So for example, the one-dimensional infinite potential well, okay, the eigenstate is like this. And n here, okay, is the quantum number. Okay, it's a quantum number. And now, although this is not important in our class, but then in general, okay, this is taught in almost every quantum mechanics class, is that a quantum state can have more than one quantum number. Okay, can have more than one quantum number. The reason is that the reason that we only have one quantum number here is because we're in one-dimensional space, right? We only have x-axis, right? So when you solve, well, so you can think about it. The equation, okay, related to this, the time-independent Schrodinger equation is a differential equation on x, right? It's one-dimensional, so that you kind of get one quantum number. Okay. Now suppose you have a three-dimensional quantum well. And three-dimensional quantum well is something real. Okay, it's actually called quantum dot. It's quantum dot is actually have a well confinement on three-dimensional, but then it's not a box. It's usually a a sphere, so it's called quantum dot. Okay, and then quantum dot, quantum well, they are real things, and then you can buy TV with quantum dot. I've said this before. They look just the same as LED, and then they cost probably 4 times more. And then suppose you have a three-dimensional potential well, okay, and then you can think about the potential well, right, is 0 when x, y, z is smaller than L, larger than 0, and then infinite anywhere elsewhere. Okay, elsewhere. So that for three-dimensional quantum well, your Schrodinger equation, okay, is the same as time-independent Schrodinger equation. It's the same as equal to minus h bar divided by 2m. Okay, this is your kinetic energy in x direction, right? The same as before, but now because you also have y and z direction, and so you have this in y direction, and then you also have this in z direction, okay? And they all act on your psi x, y, z, give you energy, eigenenergy of x, y, z. Right, this is the to solve the eigenstate. And then the boundary condition, okay, it's 0 when x equals 0, y equals 0, z equals 0. Okay, if you hit any of this boundary, you're 0, right? And the way to solve this is to use separation of variables. Okay, separation of variables. You can we can quickly show you guys here. You can assume the eigenstate psi x, y, z, psi a, x, psi b, y, psi c, z. Okay, they're separable. They're a wave function. Okay, for the eigenstate, and then you plug this back. Okay, plug this back into this equation, and then divide this entire equation by psi. Okay, then what would happen? Well, let's see. Let's do this one step by step. When you plug this back, okay, when you plug this back, the first term, okay, we pay a little bit attention to the first term, is that the differential is on x, right? So psi b is a function of y, psi c is a function of z. The differential of x has no effect on it, right? So it's typically you can treat it as a number so that you can move it in the front, so that the first term would become, let's say, psi b y, psi c z, partial x, psi a x, right? Let's write the right hand side to the left, and then move this coefficient there. So 2me divided by h bar. Okay, and then the same to the second term. Now you have psi a x, psi c z, and then partial y. And then the same for the third one. Okay. Now, one thing that the left-hand side is your 2me minus sine h bar squared psi a x psi b y. Yeah, sorry, run out of space. Okay, psi a x psi b y psi z c, okay, minus e minus 2me h bar squared. Okay, so one thing you can see is that, okay, if you divide this equation by psi, okay, by psi, divide this equation by psi, the left-hand side will just be a number, right? The left-hand side is a number times psi. Now you divide by psi, so it's a number. And then the right-hand side, okay, you divide psi a, psi b, psi c, right? This term has psi b, psi c. Okay, so they cancel each other, and then you're left here with psi a. Okay, the same apply to here. You divide psi a, psi c, and there's a psi b here. Okay. And then okay, so eventually you're left with a number, okay, minus 2me h bar equal to psi, well, differential on x divided by ax plus, okay, okay, and we've seen this before, right? So now you have a number equal to a function of x plus a function of y plus a function of z, right? There's no way that this equation can be satisfied unless this is not a function of x, this is not a function of y, this is not a function of z, but a number, right? If they're a simple number, then this equation can be satisfied. Otherwise, if this is really a function, right, you can move x a little bit, and then don't move y and z, and then the entire equation will collapse, right? So that this equal to a number, okay, let's call it a, this equal to a number b, this equal to a number c, okay? A plus b plus c equal this one. And then now you see, okay, if this equal to a number, then you have a differential equation for psi A. This equal to b, then this has a differential equation for psi B. This has a differential equation for psi C. Okay, so then you solve these three equations independently, and then you will actually get. Okay, let me write down here. For this three-dimensional state, you will actually get n1, n2, n3. You will get three quantum number, and then your energy, okay, your energy will be pi square h bar square divided by 2ml square, okay, and then you have n1 square plus n2 square plus n3 square. Okay, so what this example is telling you is that you don't, in more than one-dimensional physical system, you have more than one quantum number. Okay, you have more than one quantum number. If you are dealing with electron, usually, okay, three-dimensional. If you're in three-dimensional space, you have three quantum number, two-dimensional space, two quantum number, one-dimensional space, one quantum number, and plus additional quantum number that's spin, right? Electron can have spin up, spin down. Okay, so you have another quantum number. So typically, okay, it's the dimension you're in plus one. Okay, for electron. If you're for fermion, if you're for boson is, for example, photons that has integer spins, then you just have, for n-dimensional space, you just have n quantum numbers, okay? And you can see here, okay, one thing you can see here is that if we, for this quantum well, okay, three-dimensional quantum well, there is actually degeneracy here, right? Degeneracy here. The eigenenergy, okay, for 1, 1, 2, okay, quantum number n1 equal 1, n2 equal 1, n3 equal 2 is actually the same as 1, 2, 1 is actually the same as 2, 1, 1, right? So 1, 1, 2 means that in x and y direction, you're in ground state. Okay, your ground state looks like this, the sine wave, half of a sine wave. And then in z direction, you're a full sine wave. Okay, full sine wave because that's n equal 2. And then the energy is the same as if your full sine wave is in y direction, the same as your full sine wave in x direction. And this is called degeneracy. Okay, degenerate. Oh. Okay, and degenerate is actually, to be expected in this system because you actually have a qubit symmetry here, right? You can label this axis as x, y, z, but you can actually switch those axes, and then it's actually the exact same system, right? You're not changing, no matter how you look at it, how you set the axis, it's always have that qubit symmetry, right? So degenerate actually come from symmetry, okay, symmetry of the space, and also it can come from symmetry of time or other parity symmetry. There are many different types of symmetry exist there. And for example, for the hydrogen atom, right? We solved the hydrogen atom before. The hydrogen atom has spherical symmetry, right? It's a sphere, right? No matter how you look at it, it's actually a sphere. And then for there, okay, you can also expect there's symmetry there, and that if you read the textbook, it's actually the n number. Okay, from m and l number, those two numbers, no matter what it is, the eigenenergies are the same. Okay, and then if you want to lift the degeneracy, okay, people somehow use the word lift, not break. Okay, now people actually tend to use break again, but then it's just a wording thing. If you want to break this, if you want to lift the degenerate in the system, then what you need to do is to break the symmetry, right? Break the symmetry. So, for example, you can make, your the box, okay, the L, okay, they are not identical to each other, right? One is long, well, see, Lx, Ly, Lz. You can make Lz larger than Ly larger than Lx, right? So now you actually have a physical direction now, right? Because if you change from z direction to x direction, the electron will actually see the boxes will be different, right? The boundary, okay, is a lot tighter, and then what that would do to your eigen energy is that it will look like this. Okay, your L will become down here, and then you no longer has this degeneracy when you break the symmetry. Okay, it's the same apply to hydrogen atom. Okay, if you add, for example, if you add magnetic field along z direction, and the magnetic field can actually interact with the electron, right? And that will actually break the symmetry. You will have a z direction, okay, a dedicated z direction that's along your electrical field, magnetic field. And then also in reality, in fabrication, it's actually very difficult to make the system perfectly symmetric if you actually fabricate it, right? For example, quantum well. If you guys read the literature, quantum wells are actually spontaneously formed in the semiconductor. Okay, people have a relatively good control of how big they could be, but then for each quantum well, you actually don't have a good control. Okay, in one fabrication, one quantum well can be slightly larger than the quantum well next to it, and then also the quantum well, usually are not perfectly sphere, right? So in any system that's manufactured by human, okay, unless there's a mechanism that enforces the symmetry, otherwise you won't have the symmetry, and then you won't have the degeneracy. Okay, any questions here? Okay, no, good. The final, topic in the linear algebra section is commutation. Okay, commutator, and this is actually very, very important. It links to uncertainty principle, links to how you find eigenstates, that common eigenstate for different operators, and then it's actually the basis of a lot of things. And then given that we only have 3 people here, okay, so probably we will leave this to the next class, okay, and then I'm actually thinking whether I should adjust the final exam, okay, to some of the content I talked in class, not just on the note, so that I don't know, just to, well, I don't know if it makes sense to have people actually appear in this class because they can actually watch it on YouTube. So either way, as long as you guys learn the material, and then it's interesting in quantum mechanics, I'm happy. Okay, that's all for today, and bye guys.